Hello, Dr. Mustapha, can you see my screen?
Yes, sir. Yes, we can hear you. You can see.
Okay, so ladies and gentlemen, welcome to the YPS weekly presentations. PSI is Pharmacy Scholars Initiative. We have presentations every week, mostly during the weekend and mostly on Sundays, when people will be free to log in and listen to our presentation. So like every other Sunday, today we're going to have Dr. Mustapha Mohammed as the presenter. Dr. Mustapha is a registered pharmacist and a lecturer at Ahmadu Bello University in Nigeria. He's currently a PhD candidate at the University of Sains in Malaysia. He graduated with B.Pharm from ABU, Pharm D from UniBen, has a clinical pharmacy degree from Cyprus, and his current research focus is on clinical prediction modeling on chronic disease outcomes as prognostic and diagnostic and health economics. He develops valid, accurate prediction and decision models for stakeholders. He has published widely leading impact journals and attended many conferences. He likes football, gaming, and traveling. So in addition to this, Dr. Mustapha is someone that is well known to us, especially young pharmacists in Nigeria, more especially in Northern Nigeria. We call him Standards because of his contribution right from pharmacy school. We have learned a lot from him and he was our standard. So it will be delightful and to listen to him teach us once again in this modeling, prediction modeling in IBM SPSS, which I believe it will be very, very useful to most researchers, especially in Nigeria. So a little background before he starts on what he's going to do. Clinical prediction modeling provides risk estimates for the presence of disease diagnosis or an event in the future cause of disease prognosis for individual patients. I don't want to jump into something because an expert is going to talk about it. It's all about prediction and modeling using computer, and it's going to use SPSS IBM, which is, I believe, a lot of researchers, including mid and senior career researchers, are using SPSS in Nigeria. The presentation will demonstrate hands-on on how to develop, validate a prognostic model using statistical method of binary logistic regression. So Dr. Mustapha, I'm going to give you time now. The floor is yours. You can go ahead. Sorry, before then, like you can see that it is hands-on. So if you have your computer close to you and you have SPSS, you can just open it and log it and listen to Dr. Mustapha. Dr. Mustapha, go ahead.
Okay, thank you very much, Dr. Auwal, for this brief introduction. I think can you stop your screen?
Okay, yeah. Okay. So you can go ahead.
Okay. Can you see my screen?
Yes, I can see from my end.
Yes, we can see.
Okay. So I would like to welcome each and every one of us to this important section. So today I'm going to be discussing about clinical prediction model using SPSS. So just to set a background, prediction models help to develop healthcare professionals, other stakeholders, including patients, caregivers, to make clinical decisions. So you can imagine when you have a disease condition, for example, diabetes. So, and this diabetes, you know, we look at the blood glucose, how to control the blood glucose. So you can imagine having some like like socio-demographic characteristics like age, ethnicity, which could likely influence the outcome of the disease. So now we want to see how these independent variables like age, gender, ethnicity will influence like the disease, the outcome of diabetes, for example, blood glucose control. Now in this, what we do normally is we develop the models and then we try to classify patients based on whether they are having good or bad outcome. Then we like validate the model. Validating the model meaning you want to check the performance of the model. So it's not too different from what we've been doing previously, like we just started discussing with Auwal. We used to utilize logistic regression a lot in some of our researches. So just to give an overview of what we do when we're talking about predictive modeling, prediction model. Now, you have to, first of all, identify your research question. What are you actually trying to find out in your study? You cannot just have a set of data and you'll say, oh, I'm gonna develop and validate a model. So it all depends on your research question. If your research question really talks about developing and validating such model that you're developing, then you can go ahead. But if it is not, you cannot just use anyhow data to develop the model. So now in developing the models, you have to look at your clinical outcome of interest. What is your outcome? What is your event? Because you want to predict that event. The outcome can be mortality. It can be improvement of the disease condition. It can be reduction in blood glucose, reduction in blood pressure. So you have to identify that outcome of interest you are looking at. Then what are the predictor variables? You have to also look at what are the independent variables that you are trying to use to predict your outcome. Examples of predictor variable can be age, can be gender, can be ethnicity, can be BMI. So it all depends on your kind of study. Then of course you need to have a data set. That data set should be good enough, like should be large enough to be able to fit into the prediction modeling. There are different ways that you can be able to identify how much sample you need, but then the rule of thumb is you should be able to have at least 10 data sets for each particular predictor you are looking at. So if you have like 10 predictors, it should be like 10 times 10, minimum of 20. You can have more than that. Then after developing the model, you need to validate the model. Validation can take different forms. We have what is called internal validation and external validation. When we say internal validation, we're trying to validate the model within the data set that you have. Then the external validation, you are trying to look at an external data set, which is quite different from what you are using. So the benefit of internal validation is like you have the data set at your disposal, but then the external, you may not have the data set that readily available. Then the advantages, the disadvantage is that you cannot generalize the conclusion you are generating to when you run internal validation. But if you conduct external validation, you can infer, you can generalize that your outcome or your finding is applicable to the general population. Now, there are different methods of checking the validity of your model. The most important ones are checking the discrimination and calibration. Discrimination is when you are talking about how do you discriminate, how do you classify between those subjects that are having the outcome. For example, if we're looking at death, those subjects that are dying and those subjects that are not dying. So now you use discrimination analysis. Discrimination analysis, normally in SPSS, we use what is called the receiver operating characteristics. This receiver operating characteristics generate what is called area under the curve. So like our elementary area under the curve, we are trying to see how much of that outcome will fall within the graph. I will show you later how the graph looks like. So we are likely to look at 1 as the perfect discrimination, and then anything less than 1 is. For example, if it is 0.5, 0.5 is like 50-50 chances. So as much as possible, we want our discrimination value using the area under the curve to be above 0.5, so that you can be able to say that your model is able to discriminate or not discriminate. Then we have the calibration. Calibration is also important because it shows the reliability of your model. You want to confirm whether your model is accurate or not accurate. So in calibration, we also consider some other tests like Hosmer-Lemaitre test or the calibration plot. Later, I will show you how to look at those plots to be able to infer whether your model is fit or not. So I'm just trying to, with this, I will just show you some few difference between like prediction modeling, real prediction modeling, and then the ordinary method that we just use to identify factors that are associated with specific outcomes. These are two different studies. One is humbly led by our moderator, Dr. Auwal. In this study, we try to identify factors that are associated with knowledge of anti-snake venom. So you can see from 1A, we have conducted logistic regression in this particular study. And then if you look at 2A, we identify some relevant factors that are actually associated with knowledge. So you can see that we are using some factors, including training, I think. We have those who have not previously administered ESV. So these two factors were responsible, are factors that predict knowledge of anti-snake venom. So this one is just like an ordinary logistic regression. So in a recent work that we did, where we develop and validate prediction models, you can see here, we utilize the same logistic regression, multivariable logistic regression, but at the same time, we validated the model by checking the performance of the model using some tests. The calibration, like I said, we use Hosmer-Lemaitre test, and then the discrimination, we use the area under the curve. So at the end of the day, you'll be able to generate the factors that are associated with mortality in this case. And then of course, you have to verify and check the values of your area under the curve. If it is close to 1, then you infer that your model is valid and it has excellent performance. So also the discrimination, if the value is close to 1, you infer that the model has good performance. So now let me just, because as I said, this is going to be mostly hands-on, I'm going to open my SPSS and show you how we normally run predictive modeling. So this is just a data set. This data set is gotten from Malaysian Stroke Registry. The data set is quite big, but I was able to just cut it short for the purpose of this presentation. You can see we have like some of us who are familiar with SPSS, we have two views. We have data view and we have variable view. So this is data view. So here I have about 500. We have about 500 observations. Each row here serves as observation. Each row like this is an observation. Then each column is the variable. We have age, we have gender, we have ethnicity, among others. So normally what we do, first we have to split the data. There are different ways that you split data. It's either you split the data, like it depends. You can decide to split it 60, 40, 75, 25. But it's important to make sure that the two groups are different. So for example, if we want to split this data into 75, 25, we'll go to data, then we select cases. So because we want to make sure that everything is done at random, we cannot just divide the data set into 2. We have to divide it randomly so that there will be like equal distribution of whatever characteristics that we have. So you click random sample cases. For example, we want to divide this data set into two. The first part will be 75% and the second part will be 25%. So you type 75% here and continue, then OK. So now the data sets that we have is divided now into two sets. You can see it will generate a filter here. So this one that we are having is like 75% data. Then if you want to see the rest, you have to go back, select cases, and you select all. You said OK. So now you can see that we're having some zeros. These zeros are inferring 25% of the data, while one infer 75% of the data. So this filter is going to be important when we are trying to develop and validate the model. So now we are done with filtering. Then next is we want to develop the model. So in developing the model, we go to analyze. I don't know why this icon is covering my interface here. Okay, so we'll go to analyze, then you go to regression, then binary. So because our outcome here, we're looking at mortality, either the patient dies or did not die. So that meaning we have two options for the outcome. So we have mortality, whether the patient dies or did not die as our dependent variable. Then we have this other independent variable. We call them covariates. They are the ones that will actually be used to estimate the level or to predict the mortality. So you have to move all the variables to covariates box here. So we're going to take age, gender, ethnicity. This GC score for some of us that work on stroke is a glaucoma scale. It has a range from 1 to 15. And then this NIHS also is a severe stroke severity scale. They are all important in predicting the mortality for stroke patients. So this one, hypertension, diabetes, they are all comorbidities. The patients present with stroke, but at the same time, they have other disease conditions. So assuming we are taking this as our covariates, some of them are linear, some of them are categorical. Like for age, GC score, and NHSS score, they are linear. So they are not categorical. So for those that are categorical, normally we go to categorical covariates, and then we move those that are only categorical so that we'll have our reference to be 1. It depends. You can decide to change your reference to be the last option or the first option. So for this case, I will leave it as 1. So now, because we remember we are splitting the data, we are now developing the model. So we have to take the filter here, select variable. Then the rule is that we are trying to work on only the 75% of the records we have. Then you go to save. Here we want to check the probability of the predicted values. This will be very important when we are trying to plot our area under the curve, that's the receiver operating curve. You continue. Under the option, we need a confidence interval, of course. Then we also want to check for the Hosmer-Lemaitre test. Here I told you for our calibration, we're going to use Hosmer-Lemaitre test. So you click continue, and then you run. So like for most of us that are familiar with, some of us that are familiar with SPSS, you have your, where you run the test, and of course you have the output. So under the output, that's where the result of the test will be. So there are different, don't be confused about these tables, but I will just show you the ones that are really important for today's discussion. So now we have this Nagaraki R square is like the overall model fitting. It will tell us how much is our model very good, is it bad, you know? So we want as much as possible to have 100% of the ranking here. So like here we are having 0.104, so which is just 10%. So 10% is really very, very small. We want something close to 100% kind of. So this one is just telling us how much of our predictors contribute, the variability they contribute in predicting our outcome, which is mortality. So we also have this table. This table is really important, but then there are two ways to, when you're running a logistic regression, it's either you follow an enter method or backward forward method. So if you put enter will force all the variables into the model, but that's not what we want. We want the variables that are really important that predict the outcome to remain, while other variables should be removed. So instead of enter, we have to change here to either backward or forward. Normally I use backward. So in backward, they will put all the variables together and they will be removing them one after the other until the final predictor that is significant will be maintained. So you will see what I'm telling you. So when you go down, normally you have to go to the last step. The last step, because let me show you. The first step, all the variables are there, all the predictors are there. So you keep going, running the regression model. So it keeps removing those that are not significant. It keeps removing until it reaches the final step where only those predictors that are significant will be maintained. So at the end of the day, you would only be using this final step. You can see in the final step, we have only age, NIH score, diabetes as predictors of our mortality. So normally what we do is we'll copy this table into a fresh Word file. Because these are the results that you end up using. Only this last step. Because these ones, they are when the regression is running and eliminating those that are not significant. So here, normally, this is our p-value. This 0.001, 0.039. They are the p-values, 0.036. So conventionally, we say any p-value that is less than 0.05 is considered significant. So we have 0.01, which is less than 0.05, 0.03, and 0.036. All of them are significant, meaning they can predict mortality in this situation. So how much of the contribution, how much have they contributed in predicting mortality? That's when we use the odd ratio. Odd ratio shows you how much contribution the predictor has contributed in predicting the outcome. When we have 1.038, so meaning age has contributed 1.3038 more times low likely to contribute to mortality. So like with 1 year increase in age, like if you are increasing from 1, 2, 3, 4, 5, because it's a scale. So every 1 unit increase in age must have contributed 1.038 times chances of causing mortality. So the same thing with NIH score. With 1 unit increase in NIH score, there is chances, the odds of mortality increased by 1.030. There are other ways. You can also express it as percentage. In percentage terms, you have to subtract 1 from this. So subtracting 1 from this will be 3.8. So by one unit increase in age, must have contributed to 3.8 times chances of the person dying. So this is how to interpret this. So remember, this is all development of the model. So now we're going to use the second 25% to create the validation. So instead, you just still go back to the same interface where you put all your variables and your outcome. So instead of using 1, remember we have 0 and 1 as filter. So you use 0. So if you use 0, you just click OK. The same thing will be run again. And then you go back to, you go to where your variables are. You can see that in the validation step, only diabetes was retained as a predictor of mortality. Even though, because we wanted to see that even all the 3 that were retained in the development model should be able to be retained in the validation. Because I told you I splitted this data, so probably we may not have a very good performance, because if you want to have a very good performance, you need a very big data set. The main data set is over 10,000. So here we are using only 500. So now we have the model, the variables, and here we have only diabetes being retained. So we normally copy this also. And then paste in Word, and then you use this last predictor in your results. So how do we check for the discrimination and calibration? So as I said, in discrimination, we're trying to check the receiver operating characteristics curve. So we can plot the curve like this. You go to analyze. You go to analyze, then you go to classify, then you go to ROC. This is where the ROC is located. So now you're going to use the 2 predicted probabilities of the 75% and the 25% of the data set. Here you don't need to click anything, but make sure you click the diagonal reference and you click the standard error and the confidence interval. So you click OK. So this is the graph. The graph is looking also a bit wild. Normally, what we are expecting is for our curve to be closer to the sensitivity area, because we want it to really have a high sensitivity, high specificity. So as the curve goes towards the left side, if it is curved like this, we will have the discrimination would have been better. But here, what it is inferring is, if you look at the values for the area under the curve here, you can see the value is 61.5%. That's for the 75%. 7.4% for 25%. So had it been we have values that are closer to 100%, let's say we have values like 90, 80%. So you will notice that the curve will be somehow closer to 1, which is showing excellent discrimination. So, but here we can really say the discrimination is not that good, because it's not that close to 1. Because once the curve is close to the diagonal, close to the center, meaning the model is even very bad. So as much as possible, you cannot do anything, because it all depends on the data. So a model that has the value curve that is closer to the sensitivity show that it has good discrimination. So for the calibration, remember I told you we use Hosmer-Lomishore test, and then we use calibration plot. For the purpose of this discussion, we just use the Hosmer-Lomishore test. So in Hosmer-Lomishore test, we don't want the value to be significant. You can check the last step, which is step 8. Step 8 is showing that the value is very significant, and we don't want significant. We want a value that is not significant. So here is still showing that our model lacks the calibration, good calibration that we need. So I'm just going to show you how we report some of these modeling results. So this is how to report it. First, you report your simple logistic regression. I think I skipped this because normally what happens is when you are running simple logistic regression, it's the same thing as multiple logistic regression. But in simple, you will be putting the variables one after the other. So why is it important? Because you want to, normally before you identify the predictors, which are the independent variables, you must have consulted the literature, previous studies. What have they been using? So now you use what you have, like your predictors and what you have gotten in the literature to have your own list of independent variables. So now, because some of the variables we are not really sure whether they can be significant enough to be included in multi-variable regression, so that's why you have to conduct the simple logistic regression. So you conduct the simple logistic regression. Let me show you how to do it. It's similar procedure. You just go to analyze, go to regression, binary. So instead of putting all the predictors here, you will just be taking them one after the other. You will check age, how much of each. This one we have to make it to 1. So you'll be taking them one after the other. Like here, we have just tested each. So testing them one after the other is what is referred to the simple logistic regression. So at the end of the day, you look at the significance, those variables that are significant, then you include them in the multiple regression. So that's what happened here. So when we run the simple logistic regression, we have age, which is significant. We have gender. Gender is not significant, meaning gender may unlikely contribute to the patient's dying. We have ethnicity, significant. We have the type of stroke to be significant. Any value that is less than 0.05 is significant. So at the end of the day, you include all these values that are significant. And then in the literature, there is this cutoff point that even values that are up to 0.25, you can still include them. And even those that are not significant. For example, age is not significant, but we'll still have to include it because age is an important factor when you're looking at outcome of a lot of diseases. So we still have to include the age. But theoretically, any value that is less than 0.05, that's what you include. So this is how to present the simple logistic regression output. Then for the multiple regression output, this is how to tabulate it. So you can see that only those values that are significant were reported. Age is significant, NIH score is significant, diabetes also significant, antiplatelet use, dysphagia screening, antiplatelet use upon discharge, lipid lowering agent, stroke education, and rehabilitation. So at the end of the day, you will have a smaller number of variables because you must have eliminated others. that probably are not really contributing to the event, that's mortality that you are looking at. As I said, there are, if the value of odds ratio is 1, meaning there is no any influence of your predictor. So if it is above 1, meaning it's contributing more to the mortality. If it is less than 1, which is 0.4, it is contributing less. So maybe there is decrease in odds, 0.4 times less likely in contributing to the death event. So now, after your multiple logistic regression, then you have your model validation. So in the model validation, these are what you report. You report your discrimination. Discrimination, remember, we use our receiver operating characteristics, which uses area under the curve. So we have values like this. So you can see this value, this is actually the result of what we've done previously. You can see that the value is 0.965, which is close to 100. So this one shows that the model is able to discriminate those that died and those that did not die. The discrimination is very good, excellent discrimination, which is 96.5%. So also for the validation, you can see that we had 94.1%. So the model had excellent discrimination. This is confidence interval. Confidence interval that doesn't have 1 is significant. It's just the same thing as p-value. So the confidence interval here shows that the AUC that we are seeing is significant. Then for the calibration, we say we use Hausmiller-Muschel test for now, but there are calibration plots that you use to check for the calibrations. So for the Hausmiller-Muschel test, we don't want to have significance. The outcome should not be significant for us to say that, yes, the model has good calibration. So you can see here we have 0.05 and 0.63 for the validation. So meaning the model has excellent calibration. Then for our pseudo R-square also, which is the overall performance of the model, we also want something that is close to 1. You can see this one is 80%, this one is 74%, which is quite good. So at the end of the day, when you see this graph, you can see that the curve is close to 1, unlike the one we just generated. So when the curve is close to 1, so meaning there is high sensitivity, high specificity, meaning there is good and excellent performance, that the model is able to really show good discrimination because we are looking at the area under the curve. So there is enough, the percentage is like close to 1. So this is what you would want to see when you have a good model. So I think this is all what I have for today, unless if we have any question, we'll have enough time to discuss it further. So thank you all. I hope this is beneficial to all of us.
Thank you, Dr. Mustapha. It was such an educative and hands-on training. Can you hear me, Mustapha?
Yeah, I can hear you, sir.
Okay. So we thank you so much for this hands-on training. In fact, it will help a lot of us that are doing some research work currently. You can see you made example with our paper. Thank you for that recognition as well. So we are going to open the floor for questions. Is there anybody that have a question? Raise your hand. And then, you can even send it through the chat medium. So the floor is now open for questions. Okay, I can see Dr. Ibrahim Jato raising his hand. You can go ahead, sir. Hello.
All right. Can you hear me?
Yeah, I can hear you now.
Yes, sir.
All right, I say thank you so much, Dr. Mustapha, for this very interesting and educating presentation. I really learned a lot, especially the basics. You really tried to bring it down, I can say, to a very layman's language. We really appreciate it. I have some few questions. Yeah, number one, is it possible for a variable to be significant in SLR and finally not significant in the final model? That's the first question. Then the second one is there any, because at the beginning you talk about sample size. So is there any minimum sample size for MLR? And then final one is, I can see in the final model, I saw age and is treated as numerical independent variable. So what is the best way to treat continuous independent variables? Is it as it is or to categorize it? Thank you so much, sir.
Okay. Thank you so much, Dr. Jato. I think this is very important. You talk about, is it possible to have predictors to be significant in the simple logistic regression and then not significant in the multiple logistic regression? Yes, you can even have both ways. One is you can have a predictor that is significant in the SLR and then not significant in the MLR. Then you can have the predictor to be not significant in the SLR and then significant in the MLR. So what is happening? There's what is called a confounding effect. Normally, when you have different factors, different predictors, it is there is possibility that that predictor may not actually be on its own. It may not actually be showing you the real effect until when you combine it with other predictors. So, and then it is also possible that the significance you are seeing in the SLR is not the actual significance because probably other factors would likely influence the significance you are seeing. So let me just show you an example. Yeah, like here we have what's it called? We have ethnicity, right? So ethnicity, for example, is significant in SLR. But this, because we are looking at ethnicity alone, we are not combining it with other variables to see whether there is confounding effect. So here there is likely confounding effect that we are not seeing. So when you put them together with other variables in the multiple logistic regression, it disappeared. It becomes not significant, probably because it was just a confounding effect. But whatever we are seeing here is after adjusting for those confounding effects. That's when you will see all these variables to be significant. So that's that. So it is possible. Then we have what's the minimum sample size for the MLR? Actually, there is no any specific minimum sample size, but then the recommendation is that you should have a very big sample size, and then you should also have at least 10 data set, 10 observations for each variable. Like here that we have 1, 2, 3. So for each variable, you should have like a minimum of 10 subjects. So if you consider 1, 2, 3, 4, 5, 6, 7, like let's say we have 50 here because you have to count them individually. So you have to times 50 by 10. So meaning 50 times 10 will be 500. So you should have minimum of 500 samples for you to conduct the MLR. So for the age, you said we handle age here as continuous variable. Yeah, you can as well decide to group age into like maybe less than 18 to 30. But then the reason why we try to avoid categorizing age into groups is because by the time you are grouping the age, it will make the model overfit. So the whatever power that you have for your model will be reduced. So that's why it is important. Every variable that is continuous, try to maintain it as continuous, because by the time you are grouping them into like categories, the power of your model, the power will be reduced and it will have too much overfitting. So that's why age, we maintain it as continuous variable. And then even this GCS score, we maintain it as continuous. But then even this GSC score, you can have like more severe, mild. Even this NHIS, which is stroke severity, you can categorize it into mild, moderate, severe. So, but then because we don't want to overfit the model, we want the power to be really good. So that's why we allow it as continuous. So at any time, try to just leave it as continuous, unless you have a really important reason why you are grouping it. So that's when you can group it.
Okay, thank you so much. Please, before going to the next question, so that I can finish with my questions. You mentioned about the compounding. So
confounding,
yeah, I know there's another can I say challenges to it, that is interaction. So if you had interaction between two or more variables, how can you resolve that?
Yeah, that's why it is important to run what is called multicollinearity to check whether there is an interaction between the variable or there is no interaction. If there is interaction, definitely you have to either eliminate them both or use only one. But then I don't know whether there is any method where you can remove the interaction. Probably you can share with us, sir.
Yes, that's the best way. You only remove one, and you have to use a lot of literature to support why you are moving it. Yeah, I think that's the recommendation provided by Professor Said Hatim of US Implant, and you know him.
Even me, I'm aware about removing.
Yeah, so that's what he said. If there's interaction, he said you are dead. But the best thing to do is close your eye and remove the one that you hate. Then you now try to get some literature to support why you are moving it. Yeah, thank you so much, Prof. I really appreciate it.
Thank you, sir.
All right.
Thank you so much, Dr. Jato. This is not only a question, but also a contribution. We thank you so much. You know, you are a grandfather of statistics. So I think before we ask questions, we have a couple of chats chat history from Najib Yahya. The first one, he asks about questions regarding validation. So Dr. Mustapha, I'll read it out to you and then you can respond after.
What?
Can you hear me?
Yeah.
I'll read it out to you. Yeah. So Dr. Najib was saying, what are the internal validators? What are the internal validations protocol? And how many internal variables can you use to validate internally? Any limits on choosing the internal validators? And then he further think that you should elaborate more on the internal validation and its correlation with external validation. So,
So internal and external, I think, when we talk about internal, we are looking at the data set that we currently have. For example, this data set that I just showed. So whatever we are going to do with the data set, because we are still using that same data, we splitted it into 75-25, or we use bootstrapping, or we use cross-validation. There are other methods of validation. But then we are still using the same data. So whenever we are still using the same data, we refer to it as internal validation. So irrespective of the number of predictors you are using, it is the data you are looking at. If you are using the same data, then you are internally validating it. So if you are using an external data, maybe there is another data from the UK or from Nigeria, because this data is from Malaysia. So if I have another set of data, which is from Nigeria or from the US, that's a different set of data. So whenever I'm trying to validate my model, so you have to refer to that as external validation. There could be also temporal external validation, meaning the time interval difference. Okay, for example, this data is collected in 2022. So if I'm comparing this 2022 data with another data that was collected 2010 or 2018 thereabout, so that can also be referred as external validation, because you are looking at, there are two different sets of data. So it's either you look at it based on country, based on time, but then if you are using the same set of data, that's internal validation. So I think that's just the, for generalizability, you have to use external data. If you want to make sure your data is is generalizable, then you have to conduct an external validation. But then there are a lot of factors that may limit you to externally validating the data, even the availability of the data, ethics, a lot of issues. But then you can easily have collaborations and you externally validate your model.
Okay, thank you, Dr.
Yeah.
Does that mean you, does that answer the first question asked by Dr. Najib?
Yeah, you don't have any limit to the number of predictors you use. So if you are externally validating, just look at what they have reported, and then you try to harmonize your predictors to be like somewhat equal to what they have used also. There is no limit.
So we have two hands up. One from Hadiza. Hadiza, hello?
Let me just add a line to what Mustapha said.
Okay.
Dr. Nijo, I think the second point is, I don't think it's applicable to logistic regression. I think correlation, when you're talking about correlation, to validate using correlation, that is when the outcome variable is continuous. So in that case, we are talking about the linear regression, not logistic regression. I think Mustapha, I think is it?
Okay.
Yeah, I think when you are talking about using correlation to validate or to check whether your data or whether your outcome is okay, that's when you are dealing with a linear regression. I think in logistic regression, the outcome is binary: yes, no, disease, no disease. But logistic regression is, we are talking about linear, like blood pressure measurement, age, and co. Just an additional information. Thank you so much.
Thank you, Dr. Jata. Like I say, you are a grandfather of statistics.
All right.
So, Hadiza Yusuf, please go ahead and ask your question. Hello, Dr. Hadiza.
All right, thank you. Thank you, Dr. Mustapha, for this educative presentation. Some of my questions have been answered already by you while answering other people's questions, but I still want to understand, please, why splitting when you use 75% and you coded it as 1 and then 25% as 0? Please, I missed that aspect of the presentation. Will you please explain a bit? That's one. Then 2, like this model validation, can you please give us one practical example, either for the internal validation or the external validation? Practical example, that really, I just want to understand more, please.
Okay, I understand what you're saying. So now, thank you, Dr. Hadiza. What we are saying is, you initially want to develop a model. You want to develop a logistic regression model. That's one. Then you are not sure whether that model you built is relevant, is reliable or not. So you need to validate it. So you first develop it, and then you validate to be sure that that model that you have developed is performing, is having a good accuracy, good performance, is reliable. You can as well like recommend it for like use, they call it clinical utility. So the reason there are different methods actually, different methods of validation. You have your set of data. You can decide to split the data into 75, 25. You can split it into 60, 40. It depends all on you, depending on the size of the data that you have. So what you are trying to do is you use this 75% to build the model. You understand? You are building the model with half of the splitting, which is 75. You are building the model based on this 75%. Then you want to validate the model based on the remaining 25%. So you cannot just like build the model with the whole 100% and validate it with you can decide to build the model with the whole 100%. But then because you try as much as possible to make the data a bit independent. So the 75% data is different, it's a bit even though from the same cohort, but it's a bit independent from the 25% you are using. So that's why you split it. You split it based on 75 and 25. There are other methods. This is just one method. There are other methods. You can either use cross tabulation. Cross tabulation, you would like be taking, you have the set of data, like 100% of the data, then you will be chopping the data like in piecemeal kind of. So it's also another way of like splitting the data. There's also bootstrapping. Bootstrapping will be randomizing the data set and be taking samples at random. So all these also can be done on SPSS. They are also like easy to use on SPSS. So you are trying to use independent, you are trying to look at the data independently. You are building the model, then you are validating the model. So that's why you split. I hope it's clear.
Yes,
Thank you,
Dr.
Dr.
Can I add some few lines? Sorry.
Yes.
Go ahead. So it's a layman's language, Agile, just like when you're preparing a soup at home. So that soup, let's assume, is the model we are talking about. So you add sugar, your data set, salt, pepper, that's your data set. Let's assume oil, water. So you now keep a little beside. So when you finished, you now taste it to see is the seasoning okay, is the sugar, or the salt okay. That is like internal validation. You are validating it. If then you can now call, okay, Dr. Safia, please come and taste my soup to see if it is okay. That could be an external validation. That's a basic layman's language. So if everything is okay, if the salt is not enough, you add a little one. If seasoning is not enough, you add a little. Then, okay, the sugar is okay, it's nice, the salt is okay, the seasoning is okay, yeah, I think it's okay, yeah, that's fine. So when it is fully ready-made, then that is your final. Or when you are manufacturing a beaker, the one we use in the laboratories, when you finish it, you grade it like 10 mil, 20 mil, 30 mil. So that beaker is assumed to be like a model. So, but you can't just use it. You have to calibrate it. Like you have to use a standard measurement, 20 mils or 30 mils. Then you now try to see whether your beaker is accurate enough to measure 20 or 30 mils. So the final beaker that is already calibrated is what we are all talking about, final model. So you can use that beaker to measure. That's what we are trying to do, to predict or to measure the volume of water, the volume of liquid, or the volume of anything. So that is, that's the main basic or explanation near to what we are trying to explain. Mustapha, am I correct?
Yeah.
Thank you very much.
In a layman, yeah.
In the
because
layman.
these things we are doing, these are things that will be applied to the patient, like the community, the patient. They have like clinical utility. Even in a lot of diseases, all these skills that they use, they develop the skill, then they validate the skill. You cannot just start using a skill without validation. So you have to make sure that the skill is able to really perform excellent before you can deploy it for clinical utility.
So that at the end, if you said cigarette smoking is a predictor of high blood pressure, so you are very sure that, yes, cigarette smoking is a predictor. When you say old age is a predictor to stroke, how did you know? Okay, I use multiple logistic regression model. So that model is the one that show me age is a predictor of stroke. So based on all this validation, I can confidently say age is a predictor. So that's near explanation of what we are trying to say. So if the model is not valid, if you said age is a predictor of stroke, someone will try to question you. Like, how did you arrive at this? Or if you say young age, it's a predictor of stroke, people start questioning. But this is biologically not parsimony. How, you understand? So the model has to be valid for it to measure or to predict what you are trying, because it's something that you apply to human or like public health. So if you are doing something wrong, the consequences is very, very disastrous. Many people will lose life and there is serious loss of productivity and health expenditure. That's why the model has to be ensured that it is really, really good, because it will assist in policy making and policy direction. All these findings that we are doing in publication, in some others, like where I am, we are really using it. So if you do any wrong manipulation in the model and give a wrong answer, and they use it and use taxpayers' money to, to implement it, if it didn't work, at the end, you'll be in soup. So that is the main reason why the model has to be validated, so that at any point in time, you can have the confidence to defend anything that it came out of it. Thank you so much.
Thank you, Dr. Jato. Once more, thank you, Dr. Mustapha, for answering the questions, and thank you, Dr. Jato, for the contributions. Dr. Adiza, you can go ahead and lower your hands, unless if you have any other question again. So I saw a hand by Narendra Kumar before, but he lowered. Probably they answered the questions, but you still have a questions you can ask before we close the presentation. Any question from anybody?
I think before we close, I can see Deputy Dean, Faculty of Clinical Pharmacy, BUK. He may say some words after the after the question and answer session.
Okay, Oga is here.
Yeah, after the question and answer session, if you have something to say.
Any question? So I think probably the Narendra Kumar, his question has been answered. So the Deputy Dean, Faculty of Pharmaceutical Sciences, Bayero University, Kano, is here with us, and he's an expert in clinical pharmacy, and would like to get some comments from him and probably contributions. Dr. Umar, I please, you can say something regarding the presentation or on the topic generally. Dr. Umar, is he with us?
Hello, assalamu alaikum. Can you hear me?
Wa alaikum assalam wa rahmatullah. Yes, yes.
Sir, we can hear you.
Yeah, even though I joined late, I joined when he was explaining the ending part of the presentation, but I've learned a lot. I would like to thank the organizers for being consistent in organizing this educative session, and I would like to also thank Dr. Mustapha for doing justice to topics and all the contributors. It's really a good thing, and keep it up, please. Thank you.
All right, thank you so much, Dr. Umar. We really appreciate your support from the beginning up to where we are. Thank you so much for your persistent cooperation. Over to you, moderator.
Yeah, thank you so much, Dr. Umar. Yeah. Yeah, I'm
Dr.
here.
Auwal, yeah, I have a
Yes.
question, please. Sorry.
Okay, go ahead.
Yeah. I'll truly appreciate if Dr. Mustapha can briefly, because he has been mentioning sensitivity, specificity, if he can briefly explain what it is in terms of this prediction. Thank you.
Okay, thank you, Doctor, for this question. I think, Doctor, you are in the better position to explain this. Okay, we have discussed this, I think, some times ago when I think Dr. Shaban, he has similar study, but then his own, he was trying to develop the model using animals, then validating the model using humans. So it's somehow similar to what we've been doing. So now, if you said a model is very sensitive in the sense that if you have an outcome mortality, so the model should be able to tell you, yes, this category of patients will really die. So they call it true positive, I think, if I'm not mistaken. So true positive is meaning that you have identified the mortality in this patient, and then that mortality is really existing. You predicted the mortality will happen, and then the mortality also happened. So they call it true positive. Then false negative. When you say, okay, this category of patients will not die, and then, yes, they were identified not to really die in reality. So that's false negative. You identify, yes, they will not have the disease, and yes, they didn't have the disease. So something like that, true positive and false negative. True positive sensitivity, false negative specificity. I hope I've answered it, unless if doctor has additional information.
Yes,
I think
please,
thank you very much.
add something.
Yeah, thank you very much, Dr. Mustapha. Actually, I asked the question because, you know, in terms of the receiver operating characteristic curve, you know, you make reference, at least if, for example, like from the curve, if it is almost towards, you know, about 90% or 0.9, from 0.7 to 0.9, close to 1, you know, so there is that tendency. You have a level of confidence that the model, you know, the model is really what it sets to be. Like, it has good sensitivity. Like, the sensitivity is a ratio between the true positive, that is, let's use, I think, just for better clarity, because like Dr. Mustapha earlier said, it can be two ways, either diagnostic, you know, for example, let's assume you develop something you want to diagnose that this person has HIV or the person do not have HIV by a test. Let's say, for example, CD4 or ELISA, you know. So if, for example, the tests does the model or the diagnostic kit really really says that the person has HIV. So, and then the model is the test kit is being able to really identify that person of having HIV. That means you have a true positive. But in the case that the kit says that the person has the disease, whereas the person do not have, thus it is a false positive. So the ratio, you try to balance between the ratio of these two, you know. So the sensitivity is true positive all over the total of true positive plus false negative, you know, whereas sensitivity is a ratio of true negative over the ratio of the total of true negative and false positive. So in summary, what you are trying to get is to make sure that the model, it's actually doing what it says is doing. That's the essence of validity, because, for example, in the case of, let's say, HIV, or let me use recently, COVID-19, the test kit, the patient has COVID, and you say after testing, then the kit identify the person as not having, so the person may die, because of the test that gave an error, and likewise, if the patient don't have COVID, and then the kit unnecessarily determine the patient have, it gives the patient panic, unnecessary panic, and things like that. So these are the things that you are trying to avoid. So this is a kind of real life situations. So the validation is extremely important to make sure that what the claim about the model is true, is not just by chance. That's the whole essence of validation. The modeling is nothing but prediction, because if you say model, it seems very large, it seems frightening, No, it's just trying to use some variables to be able to predict an outcome, what may happen or what may not happen in that situation. Yeah, so I think that's the little I want to contribute in that. Thank you very much.
Yeah, I think it's very
sorry for I hope I'm not taking you back. If the model as specificity or sensitivity is like less than 50%, can you still go ahead and use the model?
If what?
That means if for example, if the model is saying that is 0.5 or 50%, that means what you are saying, it happens by chance. That is clearly what it's saying, that what you are trying, this outcome or this prediction is just by chance, is coincident, is not a good model. That is it. That's what happens. But there are other views, trying to trying to kind of what do you say, some based on literatures to support, after working, some people just try to use some literature to support some assertions. But generally, once the model is 0.5, then it is by chance. Thank you. If you have any addition, please.
Yeah, I think even from here, that's when we look at the reference. Sorry, this line, this diagonal line is the 50%. So you can remember our curve, the curve we generated is almost close to the reference line. We're having 0.6 or thereabout. So it's also really poor, like I said, but it all depends on whether the condition or the outcome you are looking, it's really clinically sensitive. So if it is clinically sensitive, so you may want to have a model that has a very high sensitivity, specificity, because you don't want to take chance. You don't want to deploy such tool and people will be dying, for example, unnecessarily. So, and again, I've seen models that go down like this. Can you hear me?
Yes, we can hear you.
Models that are even below 50%. So that's not even a very good model. As in some models, they can have their curve going below 50%. So in that case, you cannot even think about using them. But then close to 50%, it depends on the sensitivity of the clinical utility of the model. If it is very sensitive, then you cannot deploy it. Then if it is not too sensitive, then probably we consider deploying it.
All right. I think the moderator is he back?
I'm not sure.
I think the moderator has left.
Maybe you take over as usual.
Okay.
I'm at work now. Okay. Before Dr. Shaban give the closing remark, I would like just to make some suggestions to all the participants here, because sometimes we do research at home and we do mostly cross-sectional study design, and we just ended up reporting descriptive statistics like higher this, lower this one is higher than this. Sometimes in Moscow, in very, very few cases, you see chi-square test. For those who do lab, is always uncover. So I'm just suggesting, please, anyone who did any cross-sectional study design, before doing the analysis, I would really suggest if you can present his data to anyone with more knowledge about biostatistics so that he can advise him more appropriately on whether to use the data to predict or to do multiple logistic regression. Because if you have multiple regression in your paper or in your manuscript, it will add more value to the paper, and there's high chances that the paper could go through when you submit to a higher impact journal or higher quality journal. But most journals, once they see just normal descriptive statistics, there is no much innovation or novelty to the work. There is very high likely that it will get rejected. So I'm suggesting, please, our people, whenever you are doing research, please consult someone with better knowledge about biostatistics to advise you on most appropriate biostatistical method you are going to use. Multiple logistic regression is a very nice statistic that it will add more value to your paper, and at the end, you have more citations and more impact in the scientific community. Thank you so much.
Thank you so much, Dr. Jato.
Oh, you're back.
Yeah, welcome
Yeah,
back.
I lost my network.
All right.
So I can see Dr. Hadiza's hand is still up. Do you have questions, Hadiza Yusuf?
Yes, I'm very sorry for bothering you.
Okay,
please, I just want to understand something. Like, okay, after our univariate and multivariate analysis, that's for the multiple logistic regression. For example, usually we publish papers with multivariate analysis. Now, I just want to understand, is it really different from the model validation? That's one. Then two, please, for example, let's assume I want to identify factors that contribute to the development of extrapyramidal side effects in patients with schizophrenia, for example. After collecting my data, let's assume I have several variables, and then I perform my multivariate analysis, and I discovered that some factors are significant with good odds ratios. So what do I do to now validate the model? Or that's the end of the validation, apart from the cough, because at the end of this, I saw a cough, yes, and yes, I saw a cough. Is it really different from the multivariate analysis, or is it an extension?
Yeah,
thank you.
Thank you for Hadiza. Yeah, I can say it's an extension, kind of. You must have conducted your simple regression, then logistic, then you have your multivariable regression model. So then that's the model itself. So how do you confirm the validity of the model? That's when you would have to extend it to probably conduct the discrimination analysis, the calibration analysis. So those analyses, the two of them are quite enough for you after conducting them to infer that your model that you've developed is valid or not valid. So it's an extension. But then the only difference is while the normal regression that you do, you just use the whole data to develop the model. In validation, you need to devise means of splitting the data or doing cross-tabulation or bootstrapping in a way that you have a development data set and a validation data set. You understand? You have you split the data into development and validation, or derivation and validation. Then you extend to check for the discrimination and then calibration. So until when you have some certain values, like for the discrimination, you want to have an AUC, the area under the curve, to be close to 1, something like from 70% to 90%. So that's when you confirm that your model is valid. So also for the calibration, you need to have for example, Hosmer-Le test to be non-significant. If it is significant, then your model is not valid. We are not saying when you validate the model and then the model is not valid, it's not publishable. That's information. So you have already provided information that this model that you have developed is not valid. And I think it's publishable as well.
Sorry, once again, for adding some information. I think, Dr. Adiza, there is a little bit different between multivariate and what we are talking about, that is multiple logistic regression. Multivariate is like a general term for analysis such as multiple linear regression, multiple logistic regression, ordinal regression, nominal regression, factor analysis. All those ones, they all fall under multivariate analysis. So I think if you are trying to describe multiple logistic regression, I think it will be better to use the specific terminology for it. Else you confuse the listener. What do you actually mean by multivariate analysis? So multiple logistics could be just many people call it binary logistic regression or bivariate. Thank you so much.
Yeah, but I'm not sure whether she has conducted multivariate. I think she's still talking about multivariable, the binary logistic regression, because she was talking about factors that affect what's it called? It all depends. Yeah. But you are correct, sir.
All right.
Thank you so much. I can see another hand of Yahya Aliyu. Please go ahead. Yahya Aliyu.
Hello. Good afternoon, gentlemen. Thank you, Dr. Mustapha, for your presentation. I almost felt oppressed. And then Dr. Jatau come and save the day because my line of research is more of laboratory research work. And I was listening to the logistic regression, and I think if one can help us and explain it in a better way, maybe for another session, to use it instead of using our traditional multifactorial analysis, use this value, use concentration, if it first use this one, it's going to go a long way. If Dr. Jatau or Dr. Mustapha or somebody in the group can help us with a session, I personally can contact anybody who can help me in this because it's going to save me a lot of money and time. Thank you.
All right, let me respond to a little. Dr. Mustapha.
Yes, sir.
Hello, sir. Hello?
Dr. Jatau, we can hear you, sir.
Yes, sir. I think what he's trying to say is use of most appropriate statistical data analysis method. Mm-hmm. So I think it is better if you can give us time, please, we can create another special class for it to maybe do a webinar on using or selecting or choosing most suitable statistical data and statistical method for maybe biomedical research. Like if I have this data or this outcome, which specific statistical method should I use? If I have this data, this outcome, which specific statistical method should I use? Because it is not on every occasion that you use multiple logistic regression. There are heaps of them. Like I said, you can use ordinal. Ordinal when you have like high, low, medium. You can use nominal. That's just a name. Kano, Jigawa, Maiduguri. You can use a binary. Binary means two. Yes, no. There is disease, there is no disease. So it all depends on your data. You can have like ANOVA. ANOVA is totally different from, it's like opposite of what you're talking about. You can have ANCOVA. So there are so many inferential Bayes statistic. We have chi-square, so many of them. So all this one, it depends on your data and your final outcome. Like what do you want to find, and what's your final data? What is your data telling? So all those will determine which test you will use and how you do it. So I think maybe we have to create time. If Prof. Mustapha, it's a very easy thing. Prof. Mustapha will give us a more appropriate time. We can share the invitation. We can have like another session like this where we can discuss about, okay, if you have this data, use this method. We have this data, and at the end, we share some PowerPoint slides on, because I have many of them, PowerPoint slides on how hands-on, like you see screenshot, click here, click here, click here, click here, up to the end. So I think Dr. Mustapha accepted, we can organize a special class for this.
Yeah, I think we can have a look at that. And then the major reason why, if you notice, I did really dwell more on the background, like the basics of the statistical analysis that we did today, is because I think we have done this before. We've done the normal statistical methods. I think I was the one that I had a session like that.
Exactly. Yeah.
Basic statistics. So I believe that most of us were familiar with even the SPSS itself.
However, Dr. Mustapha, I think what Dr. Jachel suggested is very, very important. Like if you have the kind of research our people conduct here, so we can have a sample of data set and say, this kind of data, if you have it, is more suitable for this statistic. I think this is very important. Yes, I think we should go ahead and organize this.
Exactly. As you see, he's working from the lab. Like maybe he measured 20 rats died. Sorry for you.
Exactly.
So how will I use to know that this drug is the one that killed this rat or not? You know, all those things around. So I think Yahya Ali, Mustapha will go and look at this, and I think we'll discuss with him after this. Then, as usual, when he check his calendar and find any time he's had some space, so we can create another invitation and share it as usual. Then I think that it will be a bit interesting.
Yes.
All right.
Thank you very much.
All right. Thank you so much.
Thank you, Yahya Ali. Your questions has bring about another presentation, so we are very grateful.
Sorry, Dr. Auwal.
Yes,
briefly, briefly, please. If any, like Dr. Yahya Ali, you can check the chat box. We have an email. You can send your specific queries to that email. You know, maybe so that at least you have. Even if we are planning the presentation, we can use some of your queries to answer specific, questions that you have. So check the chat box, and then you will see the email so that you can email us. Thank you.
Thank you so much. I think we are good to go. But yes.
Yeah, just to add something regarding simple logistic regression, because it's very important. I noticed something. It's like there are two ways one can identify predictors. It's either you use the simple linear regression, simple logistic regression, or you use the individual specific test. You can use ANOVA if the groupings are more than 2, if it is 2 t-tests. So instead of going straight, I think we had this discussion with that snake venom something like that you say God power suggested, and I told you it's really correct. So it's either you go through the normal basic inferential statistics to screen for the possible predictors to be included in the multiple logistic regression, or you go for simple linear regression. I think there is Nerinda also here that is online. We had this discussion, and I told him it's quite correct to follow that.
Yes. Thank you.
Yeah, it is true, but if you do this to my supervisor, he'll reject it.
Yeah.
He must see OR. RR.
But I thought there is a way you will generate confidence interval from ANOVA.
Confidence interval is different, but he just wanted to see that.
Okay, you want to see OR. Okay.
It has undergone all those check and balances.
Okay. So I think for simplicity, it's better to just go for simple.
All right.
I think before we conclude, I'm going to hand over the presentation to the Chairman Academic Planning Committee for the Pharmacy Scholars Initiative, Dr. Abubakar Shaban. He will conclude the presentation and then he can close the session. Thank you so much, Dr. Mustapha, for this presentation, and thank you, especially Dr. Mustapha, for the contributions and all. And sorry, Chairman, before I conclude, there is a nice comment here from a Technospark 5. He said, thank you so much. This is the most educating session I have ever been. And I think this is a very good comment, and we should do more of this a lot.
And I don't know how we can trace this guy.
yeah, it means it is very impactful to him. Like
exactly.
I said, a lot.
Yeah.
So, Dr. Shaban.
Hello, sorry for the interaction.
Yeah.
I think I was the one that did this. My name is Pharmacist Ibrahim from Yobe State.
Okay.
And this is the first time I've been here, and I just came across this link, and it was so educating and interesting for me. Thank you.
Oh, as we are trying to conclude, I can see Abbas Musa raise his hand. So go ahead before Dr. Shaban take over.
Thank you for this wonderful presentation, even though I joined late. I'm suggesting, if possible, if it could be hands-on, the next one that was proposed, if it could be hands-on, I believe statistics should be somehow hands-on, so that somebody may not just understand the theoretical basis, and then when applying it to be a little bit more challenging. So it's just a suggestion. Thank you.
All right, thank you so much. The chairman, please take note and take over the presentation.
Yes.
Over to you.
Okay. Yes. Okay. Thank you very much. Due to the time factor, I think almost getting to 2 hours now, so we have to release people. Though, yeah. So that's why. Please, I will repeat this again. Just check the chat box. You can get to us through our email or get to us through our website, and then also through our YouTube channel. We are always available anywhere. Just try, you will find us there. So for more details, you will always find more interesting things, and hopefully more will come, because we have two types of presentations. We have the internal presentations within our group, and then we have ones we share with public, like this one, which from time to time we advertise it and share it on the social media. So please do check our website from time to time for updates. Then finally, I would like to all the comments and contributions are well noted. Thank you very much. So I will, at this point, I would like to thank all the participants for coming up to this moment with us, spending your time in the knowledge sharing session. And then thank you very much, Dr. Auwal Bala, for the wonderful moderation, and Dr. Mustapha Mohammed for the wonderful presentation. I can see this is, START is a very, very key in everything. It helps in, understanding or interpreting our various researches. So thank you very much for this. Normally, okay, we'll email your certificates. The certificates will be emailed to you. Thank you very much. Thank you very much. Have a wonderful day. Bye.
Thank you.
All right, bye everybody.
Yeah.